Today we have Dr. Lalita S. Kumar with us from School of Sciences. She is professor in chemistry. This program is for pharmaceutical chemistry. This is a 8th unit of this course. It deals with the fundamental portion of the chemistry. As you know, organic chemistry is a chemistry of compounds of carbon and hydrogen elements. There are more than 100 elements in the periodic table, but with the combination of carbon and hydrogen, mainly carbon and hydrogen, organic compounds are more than millions. So it is very difficult to remember this compound or to recognize this compound. To overcome these facilities, we have classified all the organic compound in different categories. For example, you know there are number of countries in the world, but each country has different type of people. For example, if we can divide the world in different countries. For example, in Asia, and there are Indian people, Chinese people, or Japanese people. They have some similarities among themselves. Similarly, in the organic compounds, we classified the compound which has similar characteristic. So we divided the organic compound into different categories known as they have different functional group. What is functional group? Functional group can be defined as an atom or group of atoms. Remember, atom or a group of atoms in a molecule which exhibits characteristic chemical properties. First class is alkane. The example is CH4, name is methane. Similarly, alkene, here the functional group indicated by carbon-carbon double bond. This is the functional group, and this is the one of the example, ethylene. There are a number of alkenes with the varying carbon chain. Carbon, in this particular case, we have only 2 carbon atoms, but you can have number of carbon atoms. In petroleum, which we use generally for our motorcycle or car or this, we have we use petroleum. But what is petroleum? It is nothing but the carbon chain. This is a combination of carbon and hydrogen only. Then alkyne. In alkyne we have carbon-carbon triple bond. Example is acetylene. Similarly, cycloalkane. This is the example of cyclohexane. Next one is aromatic compounds. Aromatic compounds are those compounds who has 6 member carbon chain, cyclic carbon with alternate double bond. It may vary. It may be of 5 member or others are, but mostly aromatic compounds are of 6 member cyclic ring. Then alcohols, or the OH group is the functional group of all the alcohol. On all alcohols you will find OH group is attached to different carbon atoms. It is in this case, in this particular case, this is CH3OH, but the carbon chain can vary from 1 to 20 or 22 or. Similarly, phenols. For phenols, functional group is this OH attached to the aromatic ring. Example is this is the one. Similarly, ether. In ether, one oxygen is attached to alkyl group. Alkyl group is CH3 or C2H5 all of you know very well about the alkyl group. We will not go in detail about regarding this thing. Then aldehydes. The functional group of aldehyde is C double bond O and H. One carbon is attached to hydrogen atom and one carbon attached to with oxygen with double bond, and other is attached to the alkyl group. This is the example. Similarly, ketone. There is a little difference between ketone and aldehyde. In aldehyde, carbon oxygen double bond with hydrogen, but in case of ketone, carbon oxygen double bond is attached with two alkyl groups. Carboxylic acid. In carboxylic acid you will find carbon oxygen double bond and one side of carbon is attached to OH group. Example is acetic acid. Similarly, esters, here carbon oxygen double bond, then the same carbon has a bonding with oxygen is attached to alkyl group. Here oxygen is attached to OH group, and in this case oxygen is attached to alkyl group. Similarly, anhydride, and so on. Now come to the very important aspect of the organic chemistry, that is the nomenclature. Aromatic compounds have following types of basic skeleton: single aromatic ring like benzene or its derivative, then polynuclear hydrocarbons, that means more than one aromatic ring is attached to each other, and then heterocyclic compound. In heterocyclic compound, first two type we have only carbon ring, but in heterocyclic compound we have ring with heteroatom. Heteroatom means other than carbon atom. The first category was benzene and its derivative. Benzene is considered as the most popular aromatic compound, most common aromatic compound. So that's why in number of cases we consider it as a parent hydrocarbon. This is a derivative of benzene. If you delete this chlorine, it will be benzene, and it is a derivative of benzene. Halogen and nitrogen group attached to benzene are prefixed to benzene. Here we call it chlorobenzene. This is a chloro group, chlorine is a chloro, and this is a benzene, so we call it chlorobenzene. Similarly, this is a nitro group and this is a benzene, we will call it nitrobenzene. And the second type of aromatic compounds are alkyl substituted benzenes, are named in two different ways. When carbon chain is less than 6 carbon chain, this is a carbon chain, remember, is less than 6 atom, the compound are named as alkyl. This is alkyl substituted benzene. This is what you call it, propyl group. Since this is a propyl group and this is benzene, so we will call it propyl benzene. But what will happen if the carbon chain is more than 6 atom? Let us see what is that. In this case, this is the carbon chain which is longer than 6 atom. If the carbon chain is 6 or more than 6 atom, then the benzene ring is considered as a substituent called phenyl, and the compound is named as phenyl substituted alkane. Remember, this is alkane. There you will find only single bond, there is no double bond in between. So this is alkane, and benzene is attached to the carbon number 2. Remember, benzene is attached to carbon number 2. That's why we will call it 2. This here we will call it phenyl. Phenyl, and phenyl group is attached to carbon number 2. So we will call it 2-phenyl octane, because it has 8 carbon atom. Other category is the benzene containing carbon chain with functional group, irrespective of the chain length. It is also considered as a substituent. Here chain length don't play any role. We, irrespective of the chain length, we consider it as a substituent. So in this case, this is a phenyl group and this is alcohol, you know it very well. So 2-phenyl ethanol, this is ethanol, you know it very well. This is ethanol, and phenyl group is attached to carbon 2. Carbon 1 is this, one carbon is that carbon which is very near to functional group. So carbon number 1, carbon number 2, and the compound will be 2-phenyl ethanol. In these cases, the compound is named either by using position number or prefix ortho. This is meta, not eta, or para. Some substituent is attached to the benzene ring, then we give one position to that particular carbon, and next is 1, 2, 3, 4, 5, 6. We can number it either this way or this way, it makes no difference. Substituent is attached to this particular carbon, and the carbon next to that carbon is called ortho group. Ortho position, not group, ortho position. This is ortho position, and this position is also ortho. Next to ortho is meta. And just opposite to this carbon, we call it para position. So take the example, some example of disubstituted benzenes. Here 2-methyl group is attached to the benzene ring. So this will be the first position, and this will be the second position. So we can call it 1,2-dimethyl. Since we have 2-methyl group, 1,2-dimethyl, and this is benzene. And the common name of this particular compound is oxaline. So this is the ortho position, and we donate ortho as O. Instead of writing full, we donate ortho by letter O, meta by letter M, and para by letter P. Similarly, in the next compound you will find the second methyl group is attached at number 3. So we will call it 1,3-dimethyl benzene, or since it is at meta position, we call it metaxylene. This is orthoxylene and this is metaxylene. Similarly, in this particular case, the second methyl group is attached at position 4. So we will call it 1,4-dimethyl benzene, and since this position is para, we will call it paraxylene. And suppose if this methyl group is attached here, then what will happen? What will you call? You will not call it 1,5-dimethyl benzene, because this position and this position is same. So you can't call it 1,5-dimethyl benzene. It will remain 1,3-dimethyl benzene. Similarly, this was an example of benzene substituted with the methyl group. Here we have 2 bromo group. Like this one, we will call it 1,2-dibromobenzene or ortho-dibromobenzene. This was a case where we have discussed about the compound which have only one aromatic ring. Let us see what happens if we have more than one ring. That we call them as polynuclear hydrocarbon. In polynuclear hydrocarbon, we have benzene ring attached to the benzene ring or aromatic ring. Polysubstituted benzene, instead of in the polynuclear substituted benzene, instead of the ortho, meta and para, the number must be used to indicate the substituent. The numbering is done in such a way to assign the number 1 to the principal functional group. The other substituents are given the lowest possible number. Numbering of polynuclear hydrocarbon is fixed by convention and does not change with the nature of position of the substituent. Example is example for polynuclear hydrocarbon: naphthalene, anthracene. In naphthalene, we will find the numbering. It starts from first here, 2, 3, 4, 5, 6, 7, 8. Similarly, in anthracene, numbering is from 1, 2, 3, 4, 5, 4. Then 5 comes to other terminal ring, 5, 6, 7, 8. Then 9 and 10.
I think Professor Farooqi has given a brief account of the nomenclature of the compounds, compounds which generally are used in the pharmaceutical chemistry. And I think before we get on to the next part of this particular session, let me just highlight a bit of what we are going to take up now. See, pharmaceutical chemistry is very important for all the students who are learning pharmaceutical chemistry. The reason being, most of the compounds, as has been briefed by Professor Farooqi also, they are all organic compounds, and the organic compounds are so numerous in number that it becomes difficult to remember them until and unless we give them a systematic name, the way we use IUPAC nomenclature. We hope that the nomenclature is clear to you. You know how to at least know the functional groups, how to name the organic, the aromatic compounds specifically, because they are the ones which are maximum used in drugs, in drug formulations. Another very important aspect which is related to the pharmaceutics and the pharmaceutical chemistry is its stereochemistry. Well, stereochemistry broadly, we would start, from isomerism. The way we have n number of compounds in organic chemistry, we have because there are so many functional groups which are involved. There are long chain compounds, there are branched chain compounds, so there is a possibility of its existence into different forms, which we call as isomers. What do we mean by isomerism? Actually, isomerism is basically existence of a compound in more than one form, and these compounds may be they have different properties, the different physical properties and chemical properties also, because the attachment of atoms or groups is different in two different isomers. So we define isomers like compounds that have the same molecular formula but different chemical structures, and the phenomenon therein which is involved is called as isomerism. And isomers can have different chemical, physical and biological properties, as I said. And the isomerism on the basis of its type can be divided into broadly two types. One is constitutional, another is stereoisomerism. Constitutional isomerism basically is related to the structural differences, when there can be a difference when the position or the functional group in the molecule may be different, and stereoisomerism relates to the stereochemistry of the compound, that is the position of atoms or groups in space. And stereoisomerism in turn is divided into two groups. We have conformational isomer and we have configurational. More important from pharmacist's point of view is actually the configurational isomerism. which gives a specific configuration to a molecule, and it is further divided into geometrical and optical isomerism. I think here I would like to highlight a little more about the stereoisomerism because stereoisomerism is the one which is basically which decides on the specific configuration of a particular molecule and therefore its drug action also. So it is very important especially for the pharmacists. And the constitutional isomerism, because you should at least know, because there are number of organic compounds involved and the isomers exist for these particular compounds also. Let us know what are the possibilities in constitutional isomerism. We have chain isomers, as the name suggests. This chain isomerism will have the two isomers which will be differing in their chain lengths. For example, butane can be represented in one way, wherein we have a straight chain as shown here, and in the other way we have 2-methylpropane. The chain gets branched, but essentially both of these are 4-carbon compounds. Then we have position isomers, wherein the functional group may change its position. For example, in 1-chloropropane we have it at the number 1 carbon, whereas in case of 2-chloropropane the chlorine atom is attached at the 2nd carbon atom. This is position of the functional group is different. Then we have another constitutional isomerism which is called as functional group isomerism, wherein the functional group itself gets changed. Suppose we have an alcohol, we have ethanol with us. This ethanol can take a form of ether also, where we have methoxymethane. This is dimethyl ether, and the functional groups, as you saw.
You want to say?
Yeah.
Number of carbon atom, hydrogen atom and oxygen are the same, but the compound is different just because of
exactly
the interchange.
The number of functional groups, and I hope that they are able to differentiate between an alcohol and an ether. That is what is depicted by the functional group isomerism. And as I said, stereoisomerism is the one which is of more significance in pharmaceutical chemistry, because one stereoisomer in when we talk of drugs, one isomer may be highly active, whereas the other one may be totally inactive and of no use to any person who is administering these drugs.
But sometimes it is harmful.
It's rather harmful. I think they must have read in their blogs also about the thalidomide tragedy, which actually relates the significance of the particular isomer in our pharmaceutical chemistry.
What was that?
The thalidomide, this was a drug which is actually a central nervous system depressant, wherein one of the drugs is actually highly active and the other one is not. So in stereoisomerism also we talk of two types of isomerisms. As I said earlier, we have configurational isomerism and we have conformational. Again, the conformational isomerism is of little less significance again for the pharmacist, because this involves the isomerism due to rotation around a CC bond, and the configurational would tell the exact configuration of the particular molecule. And in configurational isomerism we have two types. We have geometrical isomerism and then we have optical isomerism. So this is geometrical isomerism we are talking right now. Geometrical
our purpose, geometrical isomerism is important, and we will discuss only geometrical isomerism.
No, also the optical, because optical isomerism is equally important. The reason being, there again depending upon the optical activity of the molecule, the drug action is decided basically. So geometrical isomerism is caused by different arrangements of the groups around a rigid framework. And generally this rigid framework would involve a double bond. We know that.
What do you mean rigid framework?
Rigid will mean, there will not be a rotation possible around that particular bond. See, we have CC bond, you've seen, and if we had models we could show it easily. A CC bond can be easily rotated, whereas if we have a double bond it becomes difficult, the rotation is restricted, and that is what we mean by rigid framework. And if we take an example of 2-butene, we can properly, I think, rationalize this particular type of isomerism. And if we look into the structure of 2-butene, we'll see that in one of the butenes, we have the methyl groups which are, if it is the plane of the molecule, we have methyl groups which are placed on the same side of the plane of the paper, or the slide which you are seeing. Or else it can be, the methyl groups can be arranged just opposite to each other, as in the second case. So when they are on the same side of the plane, we call it as cis structure, and in case of 2-butene, we'll call it cis 2-butene. And when they are against each other, then we call it trans 2-butene. So the way we've taken 2-butene as an example of a geometrical isomerism, which we call as cis-trans isomerism also, we can take a number of examples which have double bond in between the two carbon atoms and try to see which one is cis and which one is trans. And also, sometimes we are not always categorizing them on the basis and naming them by cis and trans, because not always we have a hydrogen atom which is opposite to, or which are on the same plane. For this cis isomerism, we have 2 hydrogen atoms and 2 methyl groups, and when these hydrogen atoms are on the same plane or towards the same side, we call it cis. But what happens when we don't have a hydrogen? Instead of hydrogen, if we have any other group, still there will be a geometrical isomerism which will exist. And in that case, we have a different nomenclature, though we have not put it on the slide, but you should know that that type of nomenclature we use as E and Z. Yeah. So the E1, we are representing the E nomenclature goes for the trans and the Z goes for the cis. And the way we are trying to kind of see the groups here, similarly we see for the E and Z isomerism also. Well, optical isomerism actually is the most significant for all pharmacists, because this is the one which differentiates one highly active drug from a non-active drug. And optical isomerism is basically shown by the molecules which have a chiral carbon in them. Chiral carbon, we mean that the carbon which different 4 groups are attached. That carbon is tetrahedral in nature, and when the 4 groups of the tetrahedral carbon are different, then we say that the carbon atom is chiral. And only those molecules which have a chiral carbon, they will show optical activity. And by what do we mean by optical activity? Optical activity is basically when the molecule in solution has a property of rotating the plane polarized right to either of the direction, like it can rotate the plane polarized right to the right or to the left, and depending upon whether it is rotating it to the left or right, we call the molecules as dextro or levorotatory. Dextro when they rotate the plane polarized right to right side, and levo when they rotate it to the left side. This is how we talk of optical isomer. And when there are these molecules, there are 2 isomers, one will be a dextro, another will be levo, we say that this molecule exhibits optical isomerism, and the isomers are said to be the optical isomers. And the absolute configuration for these optical isomers is given by R and S nomenclature, wherein R is for rectus and S is for sinister. So there are actually different set rules by how we assign these configurations, and by how we come to know of the absolute configuration of that particular optical isomer. Let us see how do we do this. As we've said that the enantiomers are of these 2 types, and when we want to assign, then what do we have to do? Basically, just concentrate on this molecule. What do? We have a chiral carbon here, and we have 4 groups with us, and the 4 groups have to be numbered in such a fashion First of all, before numbering, you should be very well versed with the CIP rule for this. CIP rule was given by Kahn, Ingold and Pralog. These three scientists together, they have made a set of rules by which you assign a priority to the 4 groups which are attached to the carbon atom. So on the basis of
there
that,
are concerned blocks for them.
Exactly. You have to look into, some other blocks also. Maybe,
in the same block,
the
CIP
CIP rules are given also. And also, you can look into any organic chemistry which will give you all the rules slated into it. And these are, more or less based on their atomic sizes. This goes by the periodicity of the elements. So what do you do is you assign the priority numbers to the groups. And what do you do? The next stage is that you put the least priority group at the back, which is pointing back to against you, away from you, and put rest of the molecules in front of you. Suppose this molecule, you have prioritized the groups, you have kept the first one at behind your scene, in the sense that which will not come towards you, and rest of the molecules you have assigned the priority numbers 1, 2, 3, and then see whether, starting from the lowest priority to the highest one, you have to see where does the rotation go. If the rotation goes clockwise, you call it a rectus configuration, whereas when it goes anti-clockwise, you call it sinister, as shown here. If the priority is the other way around, this one is clockwise, of course, 1, 2, 3, you can see that the rotation is 1, 2, 3, and this is clockwise rotation, this is rectus. And if it is the other way around, that is from 1, 2 and 3 anti-clockwise, we call it as the sinister. I think this is grossly about the stereochemistry of the molecules which are involved with, with the molecules which are used as drugs also.
Okay. Thank you.
Thank you.